Hello and welcome. We are studying transistor level implementations of some instrumentation circuits. Like previously we have seen transistor level implementation of a voltmeter circuit, practical emitter follower circuit. Let us talk about few more transistor level circuits which could be interesting. Okay, so the one that we are talking about now is a linear ohmmeter. Before coming to that, let me just briefly talk about a normal, that means non-linear ohmmeter. So the previously studied ohmmeter, which we have studied, it looks like this. It has a battery. Then in series with that we have a meter and some resistance. Okay, we can have a bypass resistance also, shunt R2, and here we can connect the external resistance Rx. Okay, so this is the external resistance and this is the meter circuit. Now you know that if I know the value of this E, if it is known, if R1 is known, if R2 is known, if the Rm meter resistance is known, full scale deflection current that is known, if everything is known, then we can see the current Im, then we can observe Im and calculate Rx from it. So a quick recapitulation of this. Now, you know, this meter was not linear. Why? Okay, so for that, let's see what is the current if Rx is equal to 0. If Rx is equal to 0, this will give meter current is equal to this E divided by, this is 0, so all these resistances. All this resistance is R1 in series with R2 parallel Rm. Okay, so let me just call this R1 plus R2 parallel Rm is equal to R in total internal resistance of the circuit. So then this is equal to E by R in. Then if I take Rx is equal to say R in, then Im will be E by 2 R in, okay, and so on. If I take Rx equal to 2 R in, I'll have Im is equal to E by, so this is 2 R in plus 1 R in, 3 R in. So the relationship between Rx and I is not linear. So here it's increasing linearly 0, 1 R in, 2 R in, but the current you see, this is, if you call this is 1 unit, then this is half unit, this is 1/3 unit, so it's not linear. One can think of similar, I mean, there are a lot of similar voltmeter circuits. Okay, so one possible circuit is this, where you take the unknown resistance Rx, and then in series with that you can have a R1, you can have a voltage source, call it E, and what you measure is this voltage. Let this be a voltmeter, electronic or normal voltmeter. So, this is another possible ohm meter circuit, and here we measure this voltage Vx, we measure Vx and then calculate Rx. Okay, because E will be known, R1 will be known. So, what can I write? Vx is nothing but, it's a potential divider rule. So, I can write E divided by R1 plus Rx. So, you see, this is the reading, this is the output, and this is the unknown quantity. These two are not linear. This is again not linear. Okay. So, this circuit is non-linear. So, there could be many different, this is also non-linear. Okay. Now, we will see a circuit for linear ohm meter. And let me first tell you the idea before coming to the actual circuit. The idea is that we will use a constant current source. Okay. So, what we will, okay. So, in the previous page, here you see we are measuring the voltage across Rx, and the current that flows through Rx is generated by a constant voltage source. This is a voltage source. But if we can generate this current, call it Ix, if I can generate this current from a constant current source so that Ix is constant, then something nice will happen. You see, what I will do, I will take a constant current source. So, this Ix will be constant and known, of course, known. This is my Rx. Let me draw it slightly down, Rx, and then I measure this voltage with a voltmeter. So, call this Vx. What can I write about Vx? Vx is Ix times Rx. This is constant. So, Vx is proportional to Rx. So, this will be a linear meter. The output meter reading will be proportional to the input or unknown resistance Rx, right. So, we need a constant current source, but you know constant current sources are nothing available in nature, I mean practically available. They are realized using electronic circuits. So, let us realize a constant current source. So, this was a constant current source. Okay. So, this was the idea behind the linear ohm meter. Now, let us see how we can realize a constant current source. We will use a transistor. Okay. Okay, let me draw the circuit here. So, what I will do, so I will take this circuit, okay, so this is my transistor, and what I will do is this, I will say apply, let this be my ground, 0 volt, 0 volt, this is nothing but a potential divider, okay, this is nothing but a potential divider, and I will take it in a way such that, say, this voltage is 5.7 volt from here to here, and here I can take, say, 9.3 volt. So then this 5.7 plus 9.3 will actually be 15 volt. So I actually calculated 15 first, and then 15 minus 9.7 is 9.3 volt. Plus side, minus side, plus side, minus side. Okay, so this gives me 5.7 here. This current you call IB. This point you call VB, voltage. Okay, so assuming IB to be small, which is practical, I can write that VB is equal to 5.7 volt constant, because a small amount of current will be drawn through this. I mean, so even if IB is changing slightly, IB can change because I mean, as you discuss, IB can change, but even if it changes, this current is small. So a small thing, whether it changes or not, doesn't matter much. So I will have this voltage here unchanged, because the current bypassed is small. So, and I can generate this potential divider maybe by taking this resistance as 5.7 kilo ohm, here maybe 9.3 kilo ohm maybe. Okay. Then the current that is flowing through this is about 1 milliampere, and I am assuming this current should be much less than 1 milliampere. If not, okay, let me take this resistances bit smaller. Okay, I take 0.57 kilo ohm, here I take 0.93 kilo ohm, then this will be 10 milliampere, and maybe this current is small, much smaller than 10 milliampere. If not, I can take this resistance as small. So the point here essentially is this voltage is a constant voltage. Okay, so the point, essential point is VB is constant. Okay, using this potential divider, I have to make that sure. So I have a constant voltage VB. Okay, now if I have a constant voltage, then how much will be this voltage? Call this VE. VE will be VB minus the drop VBE, which is normally 0.7 volt. That's why I have taken it 5.7, so that this becomes 5.7 minus 0.7, so that this is 5 volt. And this is again constant. Why? Because we know this VBE is practically constant. It can be 0.6971, but not much changing from 0.7. So this voltage is practically constant. This voltage is also practically constant. So this is practically constant, or changing very less. Okay, ignore that. So now if this voltage is constant, and I will take a fixed resistance, a constant resistance, take R1 equal to maybe whatever 1 kilo ohm, constant and known. Then what I can write about this current? IE. Then IE will be V this voltage divided by 1 kilo ohm. Now this is 5 volt by 1 kilo ohm is 5 milliampere, constant, practically constant. Okay, so if R1 is constant, R1 I am not going to change. So this current is going to be practically constant, and it doesn't depend on this resistance. I haven't talked about this resistance at all. So this is constant and independent of this resistance. Call it Rx. You can now guess, I am calling it Rx means this is going to be the unknown resistance that I want to measure. Okay. Now what will be this current? Okay. So how much will be this current? Call it IC. Okay. Now IC is this current. IC, okay, IC I can write this as beta times IB, and we know this IE is 1 plus beta times IB. So this I can write beta, in place of IB I write IE divided by 1 plus beta, right? So because I is 1 plus beta times IB. So you see, beta is a constant and IE is a constant. So this is constant. Okay. So IC is a constant. So we have generated a constant current source, and this doesn't depend on Rx. Now whatever value of Rx you put within a range, of course, within some range, this current IC will remain constant, and therefore if you measure this voltage with a voltmeter, this current is constant. So voltmeter reading Vx will be IC times Rx, proportional to Rx. So this is a linear voltmeter, and let me just recap how we got this current constant. We have applied a constant voltage at the base. We know the base emitter drop is constant, so emitter voltage is constant, and this resistance is constant, so this current is constant. And practically this current and this current, they are same actually, quite close. I mean, this plus this is this plus this is this current, IB plus IC is IE, and if IB is small, I can think that these two currents are same. So if this current is constant, then this is also practically constant. So I have got a constant current source. Okay. So this is a linear ohm meter. Okay, let me just ask a small interesting question. The question is, what is the maximum range of Rx that we can insert in this circuit so that the behavior remains linear? Okay. Oh, I haven't, oh sorry, I forgot one thing. I forgot to mention that this is also 15 volt. Okay. So that means Vx is this IC, which is a constant, multiplied by Rx. That much voltage drops across this, and the remaining voltage will drop across the base collector junction. So let's ask, what is the maximum Rx measurable approximately what is the maximum Rx measurable in the above linear ohmmeter. Okay. So, the answer is very simple. So, we know VE, this point is at 5 volt. Okay. This is at 5 volt. Oh, this is at 5.7 volt. So, let us start from VB base voltage, V base is equal to 5.7, and V collector to base has to be greater than some threshold which you can get from the transistor characteristic, but it definitely should be positive. Okay, should be positive at least, and not just positive, maybe it should be more than half volt or something, some threshold which you can get from transistor characteristic, but it should be positive at least, otherwise the transistor will not act in the active region. Sorry, okay, yeah. So we need at least more than 0 volt drop, positive voltage drop, so that we get IC equal to beta IB. Okay. Otherwise, this relationships will not be true. So that means VC should be at least 5.7 volt. Maybe because I do not have the transistor characteristic, maybe 6 volt is practical now. So which is greater than maybe 6 volt. Because I am doing an approximate estimation, not precise calculation. Okay, if so, then the maximum voltage drop that I can allow across Rx, then Vx max is 15 minus 6 is equal to 9 volt, right? And this implies IC Rx is at max 9 volt, should not be more than that, and from this I can calculate Rx equal to, Rx should be less than 9 volt by IC, whatever is the value of IC. Okay. So let us take it from here. IE is 5 milliampere, let us take beta very large, then beta by 1 plus beta is 1. So then this is 5 milliampere. Then this you can write 9 volt by 5 milliampere. So this is 9 by 5 or 18 by 10, 1.8 kilo ohm. So this is the maximum resistance that you can put here, and you will get linear behavior. If you put more resistance, then the behavior will not remain same. But what you can do, so this is the maximum range. So range is up to 1.8 kilo ohm. You can change the range. We can change the range by changing this resistance R1. Changing R1. How? If I change, if I take R1, previously it was 1 kilo ohm. Now let me take R1. Let's take R1 equal to 2 kilo ohm. Then what will change? if R1 is 2 kilo ohm, VE is at the same voltage, 5 volt. Then IE will be how much? 5 volt. By here I will have 2 kilo ohm. Then IE is 5 volt by 2 kilo ohm. So this is 2.5 milliampere. And then IC is approximately equal to IE if beta is very large. Then IC is equal to beta by 1 plus beta, IE approximately 2.5 milliampere. Okay. Then this will imply that I have this relationship IC Rx less than 9 volt, which means Rx is now less than 9 volt by 2.5 milliampere, and this is equal to 3.6 kilo ohm. Check my calculation, please. Okay, so that's about linear ohm meter. We shall take one more circuit with transistors in the next class. Thank you.